heat transfer, and so this will be very quick, short, or brief introduction / review of heat transfer. So how many people in the class have taken heat transfer? Just raise your hand. Nobody? Okay. You notice I've been talking about heat and thermodynamics nonstop? Yeah. So that's why I want to introduce this right away. You're not going to have to remember all these equations, but I think to have a better understanding of heat, you have to think about it at a broader level than what you have already. So we'll introduce the forms of heat transfer. So we already talked about heat, and we gave it a definition in a previous lecture. So I'm not going to go through the formal definition of heat. But Q represents heat, and then if I put a dot above it, that represents heat transfer. And if I want to put it in differential notation, I have dq dt. Now, what is more formally used, or more commonly used, in the engineering community is this small q with a dot above it, which represents the heat flux. And the heat flux is related to Q. It is basically Q dot over A, where A is the cross-sectional area. So just to illustrate this, let's draw some circular bar. And I have some total amount of heat going through it, but at a rate. So likewise, Q dot, but I could represent this also this way, where now that is my cross-sectional area. So in terms of heat transfer, the currently a big problem rather large state-of-the-art challenge is mitigating large heat fluxes. So the computer chips, if you open up if you were to grab a supercomputer, there's several processors that are doing a lot of computations and getting a lot of work, and doing a lot of computational work. Okay? They're really small, right? But they're generating a lot of heat. So the cross-sectional area is really small. So if we think about it, computers many years ago used to be as big as this room, but now we're doing everything we could do there in a huge, so you think a huge cross-sectional area, right? Now we're doing everything on something as small as the tip of my pen. Say the same number of computations. So while the computations might be a little bit more efficient, we're generating a lot of heat, a lot of energy, which needs to be dissipated, irreversible energy, which is given off in the form of heat over a really small area. So big challenges are really large heat fluxes. So what is really large for computers? Q dots greater than or approximately equal to 5,000 watts per centimeter squared. So there's really large heat fluxes on the order of this. Now, for reference, if I take my hand and at room temperature and I dip it in a bucket of ice water, and say my hand has a cross-sectional a surface area, right, of, let's just say maybe 200 centimeters squared. Okay, what do you think the heat flux is? So 200 centimeters squared. Let's change that even more. Let's put my hand in lava. Okay, what do you think the heat flux? 200 centimeters squared. Room temperature lava, 5,000. Right? What's that? Well, you have another coefficient in front of it, but I'm glad you brought that up. We can calculate it, right? If we know something about the difference in temperature. But just for a reference, this number here is greater than my example of putting my hand in lava. This number here is equivalent to what the sun is radiating. Of course, the computers are doing this at a really, really small point, right? So we're exaggerating things because of the really small surface area. But nevertheless, we have to mitigate that much heat flux, which is a major challenge. Okay, so that's just some introduction to why heat transfer is important in a lot of state-of-the-art things. So one of your fellow classmates brought up, well, we can calculate it. And so that's what I'm going to be talking about, different ways or different modes of heat transfer. And in general, I'll just do a quick, there's 3 different ones. There's conduction, convection, and radiation. But what I'm going to do is I'm going to just draw my system, right, as some blob, and I have some surroundings. And the temperatures are at some surroundings. There's a surrounding temperature. And I'll just call it, and I'll say the surroundings are of some fluid. Could be a fluid of air, could be fluid water, but I'll just say it's, and so T surroundings, T fluid at infinity, far away from the surface of my system. And then within, my system is at some temperature. Okay? But there might be a distribution. So this side might be hotter than this side. So I might have a distribution of temperature within my system. So this side is hotter than that side. And in that case, I can have some point here, right, with a temperature, TSA, and I could have some point here, call this point A, and this point B, and this has some temperature, TSB. Now conduction is the heat transfer. Okay, so given that I made this side hotter and that side cooler, which way does the heat transfer? I'll just draw a line between the two for right now. What's that? A to B? How do you know that?
It was from hotter to cool. Areas of higher energy to lower energy.
But how do we know that?
Second law.
Yes, second law of thermodynamics. Second law of thermodynamics was different. It would be the other way around. It could be the other way around. So Q dot conduction. Heat goes from high temperatures to low temperatures. That all gets back to the second law of thermodynamics. I could also have conduction, say this way. to some point out here. Now, it could go the other way if the temperature out here was larger than there, right? But I just put the arrow in this direction. But anyways, you get the idea. Conduction deals with vibrational modes. So I have things, so I have a piece of copper. If this side's hot on my piece of copper, and this side's colder, I have more vibrations of the copper atoms over here than over there, and these vibrations are transferred along. So if I instantaneously create a lot of vibrations over here, that's going to look like an increase in temperature from a statistical mechanics point of view, and that distribution goes to equilibrate it all to have the same number of vibrational modes. So conduction is based off vibrational modes of the molecules, and then so here I have my system and it does that. Now I also can have, so let's say right here I have some surface temperature. So I have a temperature of the surface. I can also have radiation, and in that case, I have heat transfer due to radiation. So if there's a gas furnace, or if there's a wood-burning stove, if I stand, I can feel the heat. So this has to do with electromagnetic radiation, but it's still coupled to vibrational modes, but the radiative part. And then the third type is convection. And so now let's say I have a fan here, which is blowing air across my surface. So if I have my hand, I'm driving down the road, I stick it out the window, it feels cooler, right? So there's some heat transfer due to convection. And so in this case, I have a surface temperature, and I have fluid flowing over. It could be natural, maybe there's no fan there, maybe I have natural convection, this is forced convection. But anyways, I have some velocity of my fluid flowing across that. And here, in result, I have some Q.2 convection. So in equation form, let's write these out. So conduction due to, or heat transfer due to conduction is minus, in equation form, this part here is the thermal conductivity. This here is my surface area. So that's coupled back up to here, surface area. And this right here is my temperature gradient. And the minus sign here allows this is positive when the temperature further away is larger. If the temperature further away is larger, then the heat's coming back at you, right? So temperature gradient, minus sign, have it like that. So convection doesn't have, it has a similar expression, but there's some differences. In this case, I have H, which is a heat transfer coefficient, times an area, times the temperature of my surface, minus the temperature of the fluid at infinity. Surface area Okay, so when we talked about dipping my hand, right? So I could make this a small cube before I go to that. I can make that a small cube, just bring that A over here, and then I got the heat flux. Okay? But now we're talking about dipping my hand in the lava. So lava, 5,000, or let's say 4,000 Kelvin. Okay? My hand, let's say my hand is room temperature, surface temperature, roughly room temperature, before I put it in the lava. And then I have this value H here, which is the heat transfer coefficient. So we could estimate what the heat flux is, given I know the surface area, right? But then I need to know a heat transfer coefficient. So I'll just, these values range between 0.1. So 0.1 is something that, for like me blowing like that on my hand, right? Really small heat transfer coefficient, air flowing over a surface, to things on the order of, 10,000. But we have the convection part. Now, when I look back up at this picture here, I don't have a velocity in that expression. Let's go up to this. So let's take that. And then let's just blow up on this region right here. So I have a velocity distribution. Let's forget about no friction. So I have a velocity distribution. And I have my convection equation. So how would the heat transfer coefficient depend on air velocity?
The greater the velocity, the greater the coefficient.
Yeah. So when we talk about aerodynamics type things, and when you go to super high speeds and all this other stuff, we usually have distinctions between, subsonic, supersonic, right? So whether we're and then if you're taking fluids, you're hearing about the Reynolds number. But nevertheless, the heat transfer coefficient is highly dictated on the density and velocity of the fluid transferring over. So this thing's a strong function. It's also a function of temperature and pressure and a lot of other stuff. So it's really complicated, and you lump a bunch of stuff into one small number, which could be a large number, to calculate heat transferred by convection. So you could spend your whole lifetime just on trying to understand how to better calculate the heat transfer coefficient. As an engineer, you don't have to do that. Somebody else usually has documented the heat transfer coefficient for you. So we want to figure out what the heat flux is when I stick my hand into lava, and compare that relative to the heat flux at the backside of a supercomputer processor. I can do that, given that I get a relatively fair value for the heat transfer coefficient. And then the last one is radiation. This has an expression of epsilon, sigma, times an area. And then I got my surface temperature to the fourth power minus my T infinity fluid to the fourth power.
Surface or system?
Surface. So the radiation goes to the fourth power. And epsilon is a value called the emissivity. It's just a number. It ranges between 0 and 1. So there's such thing as called a black body. That's when epsilon is equal to 1. A real surface, epsilon is less than 1. If I look at a wood-burning stove, it's black. So black paint. So if I were to take a shiny say silver wood burning stove. Given it's silver, its emissivity is going to be on the order of 0.2. But if I want that stove to heat my room better, I need to increase its emissivity. So what they have is black paint. And so they just spray black paint on it, increases the emissivity at the surface, and you get a larger. If I want my wood burning stove to heat my room better, I want my stove hotter. Right? My room's at room temperature. Granted, that looks a little goofy right there. Now that I think of it. So this is to the 4th power, and this is to the 4th power. So my room temperature to the 4th power, right? So 300 Kelvin to the 4th power. I'm not going to go through the number, right? 3 to the 4th power, whatever that is, with all the zeros. So it's on the order of what? 10 to the. So at room temperature, it's on the order of 4 times 8, so 16, right? And then I got my surface temperature. So my wood burning stove could be at like 500. It could be really hot. But anyways, nevertheless, you get the idea. You want this really large relative to that, and it goes to the 4th power. So the 3 main modes of heat transfer are conduction, convection, and radiation. In this class, we just kind of use these every once in a while. What we really use is some extra modes related to phase change. So I've already talked about evaporating water or melting ice. So there's extra modes, phase change, chemical reactions, or nuclear reactions. So this class mainly deals with heat transfer associated with phase change. But we will have problems where I might give you an expression that describes the velocity of air passing over a surface, and I basically give you this equation, and I tell you what the heat transfer coefficient is, and then I tell you to assume that the system temperature is the surface temperature is the same as the system temperature. So you might calculate how the temperature of the system changes, right, by some process, and then after that, you would calculate the heat transfer. So I might do some, we might have problems where we have to apply things like this, but really we do thermodynamics to tell us something about the temperature and pressure of the system, and then we could use other things to couple in the heat transfer. Really, they're coupled together. So real problems, you have to do iterative methods. So any questions on that? That was my really, really quick introduction to heat transfer. So since we were talking about heat transfer, I'll leave this up for one more second. Okay, so if you're driving down the road and you stick your hand out the window, it feels cool. Okay? So if you lick your hand and you do the same thing, it feels even cooler. So we probably all done something like this and then held our hand out the window and it feels even cooler. So in that case, this phase change part, because now we have evaporation, is coupled within this. Does that make sense? So I could just have pure air in that type, and the faster you drive, the cooler it feels. But I could get my hand wet, and then I also have evaporation. If everybody I'm sweating now, so I can just do this and I feel it, right? But you can see that this heat transfer coefficient has a phase change part into it. So then the heat transfer coefficient increases even more if you're having phase change.